Good evening. Our today's speaker is Professor Boris Kruglikov. As you see, he will speak about geometry or about rational integrals of geodesic flows. Boris, you are welcome. Please begin.
Okay, thank you very much. It's always a pleasure to talk on this seminar. So just a basic word to set up. So n will be dimension of manifold. Okay, so G will be metric. To get Hamiltonian, we go to cotangent space, and Gij with upper indices is matrix inverse to Gij with lower indices. In other words, this gives a metric on T star m, while there's a metric on Tm. Okay, 1/2 is conventional, useful, and then we write Hamiltonian equation. So that in terms of x and p, it's like this. And if you would like to pass from cotangent space to tangent space, then we have to raise indices. So here coordinates x, I upper index, and for pi it's momenta lower index. And as usual, by repeated indexes there is summation. And then the raise index here, passing from T star m to Tm. Okay, so it's good exercise to check that we get the standard equation for geodesic. So this is equivalent. Okay, and then standard thing that function on cotangent space is an integral if it's a derivative along the flow, which is the same as Poisson bracket. And here are some agreement, disagreement with plus minus with different sources, but it doesn't matter because it's equal to 0. So that's standard Poisson bracket. And again, summation by repeated index. And legal integrabilities exist of n integrals, which are in evolution and almost independent everywhere, where the first integral is just Hamiltonian itself. And usually people write here so for function something rho c infinity, but that's actually what is going to be changing here. Okay, so let's overview. So usually integrability of dynamical system of ordinary differential equations is considered globally, contrary to PDE, where it's mostly local story. So let's say briefly about global story. And globally there's global topological abstractions to integrability, and there are several names related to this. I named Kozlov, Kolokoltsev, Paternain, Taimanov, Matveev, but there are more names, of course. And here are samples of results. And the first results go first to Kozlov and then a stronger version to Kolokoltsev, that if is a surface, closed surface, dimension 2 a manifold of genus G, and if genus is greater than 1, then whatever metric G is, it's non-integrable geodesic flow. And then there were results of Taimanov that generalizes, and here are a couple of results of Taimanov. So if pi1 is not almost abelian, which means it doesn't contain an abelian subgroup of finite index. So if it's not almost abelian, then the flow is not analytically integrable. Or Taimanov also formulated doesn't exist geometrically simple integrals. Or another criterion, if first rational homology group has dimension bigger than dimension of manifold, that's the same conclusion. Okay, then there were several works by Paternain, and in particular, he showed that if topological entropy of the Hamiltonian system is positive, then it is not analytically a Bott integral. So first proved in dimension 2, and then with some other conditions of higher dimensions. So here actually matrix plays a role because that's actually the dynamical system on manifold of unitangent vectors. So spherical bundle or original manifold M. Okay, and here are a few more examples. So if rational homotopy groups have bigger dimension, but here all possible from 1 to infinity, then it's non-integral, but in stronger sense, Stekel-Benenti sense, also called L system of quasi. This system appears in separation of errors. Very similar story, homological criterion, but here's bigger estimate. And of course, here's H star, it's finite range for star, summation by star. And one more, if Euler heuristic is negative, then the same conclusion. So note that any of these later things implies a form. I think it's kind of generalization. This is two-dimensional, but actually any of this implies the first. But one has to be also careful because there are counterexamples here. So for example, if you talk about smooth here, then it will not be true. So it's possible to have positive logical entropy and smooth integrability in the usual sense. So that's the first example was by Boris. Then was examples by Paternai and Butler. When we talk about local, then actually here's folklore theorems that locally every Riemannian or pseudo-Riemannian metric is integrable. And that's a simple statement which follows from existence of geodesic coordinates. So basically, whenever geodesics of unit length enters some neighborhood, it has to exit, and we can talk about geodesically convex neighborhood. However, the integrals which we construct in this form, they are analytic in a complement of zero section. So locally means, of course, there is some small neighborhood U inside M, and going to be geodesically convex, but we have to remove, because we construct this integral first on unit sphere bundle, and then we extend by homogeneity. So it's not extendable to zero sections. What about good integral? Okay, so here a theorem, another folklore can be found on Whittaker and even on Darboux. So if geodesic metric allows integrals that are analytic near zero sections, then also they allow polynomial integrals. Okay, so let's talk about polynomial integrals for a bit. So they are also known as Killing tensors. And for those people who like things in indices, they denote it like this. So D tensor is a tensor with upper indices, and there are D different indices and symmetry with respect to this. In other words, they are sections of D symmetric power of tangent bundle. Okay, but since we talk about metrics, actually, tangent or cotangent doesn't play a role because we are free to raise all over indices. So here, how it's written as integral. So I don't have place here for x, but these things depends on x. This coefficient depends on x, and there's summation. So it's p momenta, so it's polynomial in momenta of degree d, and something smooth, for example, in base coordinates x. Okay, so the condition that it's an integral is equivalent to the following. So first of all, we can, instead of pi, we can consider del I, so corresponding vectors corresponding to momenta, and then the condition will be the following. We take this tensor, we lower indices, we differentiate one's covariant, and we symmetrize by all indices. So it was already symmetric by indices I1 to ID, but when we differentiate this kind of tensor, so we make bigger symmetrization. So parenthesis around means symmetrization. Okay, that's equal to 0. That's condition for killing tensor. And then a theorem which proved with Vladimir Matveyev, Vladimir Sergeyevich Matveyev, that locally generic metric doesn't admit, so it's non-integrable in the polynomial sense. So it doesn't admit any non-trivial killing tensor. We have to say non-trivial because, of course, Hamiltonian itself is killing to tensor, and its powers will be killing for tensor and so forth. But these are non-interesting, and everything different from this will be called non-trivial. I indicate here C2 because the first intention when one sees the theorem is to say, look into this system here. It's actually overdetermined. And so one should just go and compute prolongation of the system. And it has entries, metric G, coefficients of metric G. So for generic entries, there will be no compatibility, and after imposing compatibility, we get completely inconsistent system. However, in doing this, one have to differentiate a lot. And first of all, it's difficult to control. Second, it's almost impossible in practice to fulfill it. and 30 will need higher regularity. Here's just C2. Okay, so it's a bit different argument here, and I will reuse this argument later. Okay, existence of local Killing tensors. Actually, they always exist, and we would like to say something like irreducible. Because of course, if you have one polynomial integral of degree d1 and another of degree d2, you can multiply them and get polynomial integral of degree which is sum of d1 plus d2. So those would be called reducible, and those which cannot be obtained by linear combinations and products from integrals of lower degrees should be called reducible. So theorem which goes back to Kozlov, it was mentioned in his book, and expanded proof actually is in the paper by 10, that on surfaces locally there is matrix of arbitrary degree which are reducible. So here is surface, and the story is the following. So let's explain what the proof very shortly. So let's write the metric in the terminal conformal coordinates. Okay, so it's dx squared plus dy squared if it's Riemannian. If it's Laurentian, this in parentheses will be dx squared minus dy squared or dx dot dy. Doesn't matter. It's important that there's only one function here, which is factor. Okay, and then the integral has d plus 1 functions. ud is a function of xy and so forth, and px, py are momenta dual to x and y. So previously I denoted them by p1, p2, but okay, that's just another notation. So in the right condition, it will be PDE of first order, and how many PDEs it will be here? So h is quadratic in momenta, I is of degree d in momenta, therefore put Poisson bracket has degree d plus 1 in momenta, and it has d plus 2 coefficients, and there are precisely d plus 2 unknowns. So it is actually a determined system. One has to check that it's some determinant is not zero, but it's determined and can be written in Cauchy-Kovalevskaya forms of solutions. Actually, stronger story is true that it has the form of so-called semi-Hamiltonian systems in 1.5 dimension, and that's so-called rich system of incarceration laws, and was explored by Bialy, Mironov, and then Pavlov and Tsaryov, and then also by Agapov. And that's a way to construct explicit solution for such system. However, one has to stress that when we construct explicit solution, we simultaneously get a metric and an integral, right? So metric is not something given. If metric is given, the system is overdetermined, and this is not applicable. So by doing this, you construct examples of metrics with integrals, but well, metric is whatever you get. And let me remark that clearly the above statement should be true also for higher dimensions, and more or less you can take the product okay, so product has integrals, but okay, but there should be formal proof. That's not, I haven't seen exactly that such thing exists. Semi-Hamiltonianity property is purely two-dimensional, so this doesn't change your lives. And another thing is that this approach, which is here, actually just governs one integral. And in more dimensions, we need more integrals, which will be in evolution. That's a completely different approach. So this doesn't work. As mentioned, there are some examples coming from this semi-Hamiltonianity, explicit examples, but also there are lots of examples coming well, from physics, School of Fomenko, Bolsinov, Matveyev, Topalov, they explored, also Kiyahara in Japan, so they constructed a lot of explicit examples. Okay, so now counting of Killing vectors and tensors. So we say about Killing tensors in general, but if degree is 1, if it's linear integral, then we could talk about Killing vectors. Okay, so one theorem is a very old one, started with Ricci, Bianchi, Fubini, then Cartan, then Igor Egorov. And that's the maximal number of linearly independent Killing vectors. on manifold of dimension n is n plus 1 choose 2, which is n times n plus 1 divided by 2. And then there's gap, and there's nothing in between, no isometry dimension possible until n plus 2, n choose 2 plus 1. Okay, so below this number and above this number, it's not possible to have metric with this isometry dimension. Okay, so that's for general n, and there's two exceptions. N equal to 2. For n equal to 2, this number is 3. This number is 2, but 2 is not realizable. So there's gap. Oh, that's actually wrong. At this point, when n is equal to 2, submaximal should be 1. Okay, sorry for this. Actually, this 2 appears a bit later. That's maybe why it's a mistake here. Okay, and another exception is n equal to 4. And then the maximal is 10, a submaximal is 8 or 7. So 8 in signatures Riemannian and neutral, and 7 in Lorentzian signature. Okay, so this submaximal story is pretty much classical. So let's denote for a metric G the linear space, a vector space of polynomial integrals of degree D by this symbol, K and D G. Okay, so now when D is greater than 1, the story is much more complicated. But still, there is maximal bound for dimension of this vector space. It's always finite dimensional for finite D, and here's the bound. Okay, so there are some number of factorials. It's integrated, and let's remember this number, lambda and D. It will appear a bit later. So this bound is sharp, and it attains on space form and only on space forms. So matrix of constant curvature, 0, positive, or negative. Okay, so some related results. One can also look not only for Killing vectors of tensor, but also for conformal Killing tensors. And similar bound was obtained there by Eastwood about 20 years ago. The equation for conformal Killing tensors will pop up soon. So basically it's okay. So basically it's very similar to this equation. However, when we do this chemistrization, we have to remove all possible traces. That's it. So then also, so here there are space forms, right, and that is maximal. But also people were recently interested in Killing tensors of symmetric spaces, like complex projective, quadratic projective, so forth. So there are recent works by Eastwood, Matveev, and Nikolaevsky. Also, for some of those things, for example, for conformal vectors, for conformal Killing vectors, we also know the submaximal symmetry. Maximal was given by okay. So for conformal Killing vectors, it's actually maximal was known before Eastwood. So Eastwood contribution was for higher degree conformal Killings. But for conformal Killing vectors, maximal was known, and submaximal, okay, it was done in my work with Demiston some time ago. Some partial case in dimension 4 was first computed by Dunajski, and then in general we solved it with Demiston. It should be said that for higher rank Killing tensors and conformal Killing tensors, the problem of gap is completely over. So when for degree D equal to 1, it's completely solved. Even for D equal to 2, in general, it's completely unknown. Some very partial cases for small numbers. Okay, so let's briefly look to non-polynomial integrals, and here's a Hamiltonian which actually doesn't come from metric in general. F0, F1, and so forth of P are just some functions, and this is affine in X's. Okay, if I write that I will be function of P, just momenta, no X's at all there. And if we write that it's an integral, it's a very simple equation. Here it is. So which tells that psi is an integral of a vector field. So it's first order PDE, linear, and can be really resolved in many cases. For example, if you take n equal to 2 and f1 and f2 to have common factor f of p and then p1 in some power and p2 in some power, maybe some integer, some real factor here, then solutions are of the following form. So function of this thing, or function of this thing, or function of this thing, depending on a and b. So we can look at just as this in very parameters a and bk, and we see are in different things. We get polynomial or more complicated rational, or maybe algebraic analytic, or even non-analytic and not even meromorphic functions here which appear. So which tells that sometimes we maybe need to extend our classes of equations. This is possible to get here actually metric case. So it's possible to get geodesic. For example, this first function can be taken quadratic, and the second function, f1, f2, and so forth, should be taken linear. This will be so magnetic Hamiltonian, but yeah. But also possible to convert it by certain tricks to usual geodesics. So particular metric examples before, for those cases which I say P0 quadratic, P1 linear, P2 linear, we are considered by Maciejewski-Przybylska, and later, but it's actually looks like special case, Aoki-Kurito model. Okay, so why I also mentioned these other things, it's sometimes good to look for polynomial integrals, but they may not be enough. So of course there are nice cases when everything is polynomially integrable. But for instance, some years ago, recently there was interest in so-called conformal geodesics. The conformal geodesics is not Hamiltonian system. It is not second but third order. And in the simplest interesting case on three-dimensional manifold, or for example on general sphere with different momenta of inertia, then there are all but one polynomial integrals, but the last integrals required for integration is actually not polynomial. So sometimes people have to accept. And the first expansion, which is very reasonable, is to keep algebraicity is rational. Okay, so rational integral of by degree R S is a ratio of two polynomials. Okay, so we say one polynomial, and when we say polynomial, we just refer to momenta coordinate p. So in p it is polynomial, and x comes through in smooth way through coefficients or in analytic way. Okay, so degree of numerator R homogeneous, degree of numerator S homogeneous. People also consider inhomogeneous polynomials, division of inhomogeneous. That's a bit different story. Okay, so I will consider inhomogeneous. And okay, we can say P and Q are relatively prime because they have common factors. We can remove these common factors. So here also an important thing to say that if we are just smooth, there can be like domains when there's common factor and then some other domains where there's no common factor. So you actually cannot cancel, even though sometimes you see common factor. Of course, in analytic context, it's not possible. So sometimes we have to strengthen the coefficients to be analytic in order to exclude such strange behavior. Okay, so denote the space of such integrals of by degree Rs on n-dimensional manifold with metric G by this long R of G symbol. This space is no longer linear. Okay, so that's certain, we hope meaningful, but we'll discuss. Okay, so first theorem, also by Kozlov, so that actually locally there are such things. So we can always find a metric, so that will be rational integrals of by degree Rs, which are also irreducible. And now we have to actually specify what means irreducible. It's a bit different than for polynomial. It means it cannot be taken as product of rational integrals or combination of such products, where in each case by degree will be r prime s prime, and r prime will be less than r, and s prime will be less than s. So it's actually strict inequality between by degrees. Okay, so that's what means irreducible. So both degrees, like first component, second component is less. Main target of today's discussion is to understand the space, and the conjecture is the following. So this space of rational integrals of by degree Rs is finite dimensional and is dimension bound by these for the flat metric. Okay, so here parameter is metric G, this functional parameter indeed. The story is local. It's already a local story. It's complicated, and the statement is a space of such thing. Well, finite dimensional and dimension is bounded by this. Okay, so I cannot prove this conjecture in full generality, but I can prove part of it. Namely, I can prove finite dimensionality part, and I will explain it. And I can also compute dimension of this thing for flat metric. Okay, but the whole story is still open. Okay, so in order to in order to approach this problem, I would like to introduce the following notion. So consider a function k of xp, which is polynomial in momenta of degree d, and coefficients are smooth analytic functions of x. So such a function will be called a relative Killing tensor of degree d if it satisfies this equation. So here's Poisson bracket. So h has degree 2 in momenta, k has degree d in momenta, therefore Poisson bracket has degree d plus 1 in momenta. And I would like that this function of degree d plus 1 is factorizable. K has degree d, therefore L has to have degree 1 or linear. Okay, that's function called cofactor. Okay, so the usually, of course, division is not possible. So here we require division. Geometrically, it indeed means that Hamiltonian vector field corresponding to H will be tangent to the submanifold k equal to 0 in cotangent space. Actually, it's better to think about this condition in complexification. So if everything is like its coefficients analytic, there's no problem to do complexification. And then you can, of course, complexify M and K, and you'll get non-empty manifold. Because of a real world, this submanifold may turn out to be empty, if it's sum of squares or some other even powers, for example. Okay, so then you will not see geometric part of it. Okay, and this concept, which I called relative Killing tensor, actually appeared before. It's not new, but was like generalized Killing tensor, the Wu polynomial. So it was called differently by different people in the literature, but also sometimes there was restriction. For example, the Wu polynomial, some people required that k of xp is polynomial in everything, in x and in p. So I prefer the nomenclature above, this relative Killing tensor, because it's actually sounds analogous to relative invariance in the theory of group actions and invariance of group actions. Namely, here the group R is just a Hamiltonian flow. So its action on our manifold is actually on cotangent bundle is through the Hamiltonian flow. And then it precisely becomes just standard definition for the section of relative invariance. Okay. Okay, so that's definition of relative Killing tensor. So now that if k is relative Killing tensor, think about the geometric definition that Hamiltonian vector field is tangent to k equal to 0. Then actually, if you multiply a function k by non-zero function, which depends only on base variables, on x's, right? So phi is function on the base lifted to cotangent bundle. Then this is also a Killing tensor. Okay, the cofactor then changes by exact form. So look back to here. So we multiply k by exponent, then we apply Leibniz rule, and then L will be changed by a differential of phi. As it is written here, these are functions on cotangent spaces, so actually L function linear momenta, so it's actually vector. Okay, but due to metric, we can identify vector and covector, and when I write things like this, L plus d phi, I think about L as covector, or as one form. Okay, in particular, K is locally conformal to a Killing D tensor if DL is 0. And in this formulation, this two-form DL, of course, is invariant, and it plays a role or analog of the chain curvature in web theory. Well, usually it's in dimension 2, even though what I'm discussing is general dimension. Actually, web theory in dimension 2 will appear later in slides. Okay, so we don't want to distinguish between K and non-zero functions and K. So we would like to identify that's conformal to scaling, doesn't make any difference. So we identify the pairs KL and exponent phi times K, comma L plus d phi. This will be considered the same. Okay, so it's actually instructive to compare the above definition with the definition of conformal Killing tensor K. So equation for conformal Killing tensor, so one of them I say you take the same definition as Killing tensor, but you remove all possible traces, contractions of the metric G. Okay, and then you get the Kaftan part of the corresponding equation, and that will be equation of conformal Killing tensors. That formulation through covariant derivative. But we can also formulate it through Poisson bracket. So we take HK, and now it should be proportional to H. So going back here, so Poisson bracket of H and K is divisible by K, and here Poisson bracket of H and K is divisible by H. Okay, again, counting degrees in P, H degree 2, K degree D, so Poisson bracket degree D plus 1, H degree 2, therefore L has to have degree D minus 1 in P. Okay, so so one has to think that, okay, so here if you look to this, that's linear equation on K. Okay, so that's equation on K, all coefficients on K, and that's linear PD equals to overwritten. So here, that actually inhomogeneous equation on K, and you have to eliminate L. And one has to say, that's maybe possible actually to, well, when you eliminate L, maybe it becomes actual nonlinear, but no, it will be just removing certain CZG, and so it's still linear. Okay. So let's denote the space of relative Killing tensor with cofactor L by K and D GL. So I just put additional L, which will signify for those relative Killing tensors. And D will stay for degree in P, in momenta. Okay, so by what we discussed, the corresponding PD linear, so solution space is linear. Okay, and this change, conformal change, well, we'll write in this form for the corresponding vector spaces of solutions. Okay, so the first statement is that actually counting dimensions is the same as for Killing tensors. So fix L, and then dimension of this vector space is bound by the same number as for Killing D tensors. Proof is very slight modification of the standard proof for Killing D tensors. So let me briefly go through this. And the idea is that actually, if you look to equations are not the same, but their symbols are the same. And therefore you think, perhaps they can be brought to very similar form, and that's correct. So equation is actually, first of all, as we say, so it's one jet space, and the variables are coefficients, right? So it's actually the Killing D tensor is section, as I said, of d-symmetric power of tangent manifold. Okay, so if you choose a basis, of course, you get a lot of components, and that will be PD on those components. So components, I will denote K with lower index. Lower index is multi-index of length D. I1, I2, and so forth, ID, where I run from 1 to dimension n. Okay, so here's our PD. So that's K sigma is a component of Killing D tensor. We do covariant differentiation by I. previously wrote nabla I, but sometimes people also write I from the right hand side, and you symmetrize by I. Okay, and removing traces actually means, but now you remove traces not with the help of metric, not with the help of h, but with the help of k. So you remove everything which is proportional to k. So you multiply k by linear form, and you again symmetrize indices on the right hand side as well. So just look into this thing. Right hand side is zero order in k. So really important for symbol is left hand side. That's where first order is. And so you can look to this one and just look for characteristic variety. And as I said, it's the same as for standard Killing tensors, because for standard Killing tensor L is zero. You have zero on the right hand side. So exercise characteristic variety of this thing is zero. Oh, sorry. Well, it's zero if affine, but if you think about characteristic variety as projective variety, then it's empty. In a fine version, it is zero. This means that system is finite type. This means that space of solution is finite dimension. Okay, but how much? How many dimensions do we have? So we have to do prolongations. We start differentiating this equation. Okay, when we differentiated k times k is prolongation, we get kind of this equations. Here I differentiate by multi-index kappa of length k. Okay, and that left hand side is clear. I have this, and right hand side I have, well, okay, some complicated thing of this kind, because here's Leibniz rule, we differentiate a bit here, differentiate a bit here, therefore I get binomial. Yes, a bit difficult with notations here. Left hand side is clear because it's symmetrization here by d plus 1 index, sigma of length d and I of length 1. But here I have to do the same symmetrization, but there's nu in between. Okay, so that's nu is kind of, but symmetrization still happens by just I and sigma here. So don't know good notation for this. So I have to write it with words. Okay, maybe a good notation here will be to write nabla sigma before. It will solve in this case, but then it doesn't solve in some other cases. I want some other formula. Anyway, when we come to order k equal to d, okay, then we have actually same number of differentiations here, and so same number of indices kappa as indices sigma. And system becomes actually determined. So we will be able to express all k sigma covariant derivative by tau, where I forgot to write it, where length of tau is d plus 1. Okay, so here it should be some function, complicated algebraic expression of smaller k mu nu. So nu here multi-index of length less than d, and yeah, and that's numbers. Okay, so this be able to express all derivatives of k sigma of sufficiently high order. So that's complete system of Frobenius type, and then one has to go and study compatibilities, cross derivations and other stuff. That's very involved. But the system is compatible at least for g equal to g0. And in this case, the dimension of this Killing tensor is the same as we take just L equal to 0. And so we get this number from before, lambda n, where there was 6 factorial formula. Okay, so in fact, a natural conjecture would be that this is attained only for G0, or actually for constant curvature. But then one has to actually check that this compatibility conditions imply this. And in some lower degree dimension cases, I check this, but in full generality, I couldn't. So this is kind of still open. A remark that the last thing when I compute dimension in this proof on the last thing, this last computation here, actually it uses projective invariance of the equation. So when we just talk about Killing tensors, in case L equal to 0, that's known as projective invariance of Killing equation. And the argument is straightforwardly generalized to our more general case. So here's the argument. So let's change connection. Okay, so we have connection, Levi-Civita connection, right? Because we start with it, but actually we can forget about it. So we can change it by one form, upsilon is one form, and here's 1, 1 tensor, and that's symmetric tensor product. So this thing will be 2, 1 tensors. That's how we change connection. And that's called projective change of connection, because doing this, the space of geodesics is the same, even though geodesics will be reparametrized. But as unparametrized probes, they are the same. So it is possible to do change of this thing also T-temp metrizability. That will be metric connection for some other metric. But okay, we don't need it. So then we write our equation. Okay, so things with heads to the left, right? So differentiation with respect to new connection and new L hat, and things without this to the right, and we can actually easily solve it, and we take L hat to be L minus epsilon. I recall that everything here, L hat, epsilon, are just linear, one forms, all vectors. Okay, so projective invariance actually tells us, and in a flat case, it just tells us that the space is representation not of group SO, which one might think, because we talk about metric, right, of the analysis. But this expansion actually, when we say we can actually forget about it, it's metric, metric connection, but talk about general connection. It tells that we talk about general projective group. So it's algebra SL plus 1 or kind of local group SL plus 1. It's a bit depends on whether on the model we talk. If we talk about Euclidean space, it actually will not act as group, but on the local action of this group SL n plus 1, right? But we can complete it, compactify it to spherical model, then it will act. It will be not SL but PSL. Okay, so the representation of this group, which will be responsible for this, will be this. So if we take, so this group is called AN, right? And it has Dynkin diagram as string with white dots and n white dots. So we put cross on second, and we put integer d there, and zeros otherwise. So marking weight of this will be 0d 0 0 0 0. In other terms, we take second fundamental notations with multiplicity d, and that's the corresponding representation. Okay, and since we know representation, then we can exploit wild dimension formula, and we get the dimension of this thing is precisely this lambda nd with 6 factorial, and that's the dimension of space of V tensors for constant curvature metric. Okay, just a bit more general words about relations of Killing tensors and rational integrals. So here I assume analytic in excess, polynomial in P, but analytic in excess, because I don't want to have trouble with notariality and with divisibility property and so forth, because things I mentioned before. Okay, so ring of relative Killing tensors has double gradation, so it's graded by D and by L. Namely, if we multiply such two things, then we have additions of degrees, and we have additions of cofactors. Okay, and if we have two relative Killing tensors with the same cofactor L, but degrees can be whatever, R and S, then we can divide them. Cofactors divided the same as multiplying in reverse order, so then cofactors will subtract, and we get actually that is cofactor 0, and in other words that it's just Killing tensors, not relative but absolute. P over Q will be absolute, but it's no longer Killing tensors indeed, because it's not polynomial, right? But it will be integral, not relative but absolute invariant of the corresponding Hamiltonian flow, so it will be integral. So that's rational integral of by degree Rs. Okay, so here are a couple of easy statements. So first, whenever we have relative Killing tensor, and if it's factorizable, then every factor is also some Killing tensors for some smaller degree d and some different cofactor L. Okay, and if we have rational integral P over Q, of by degree Rs, then P is going, and Q, they both are going to be Killing tensors of the same cofactor, well, sample cofactor, right? And well, their degrees will be RNS. Okay, so let's study a space of such P and Q. Okay, so we have the same cofactor and well, degrees whatever, right? So okay, we would like to divide them, therefore they are not identically zero. They should be not identically zero here. These polynomials, especially over C, of course, can have zeros, and we don't want common divisors. Okay, and when R is equal to S, we actually would like that they will not be proportional; they will be linear independent. So we would like to have this, because if they're independent, divide and we get constant. Not interesting. Okay, so we call cofactor admissible if the corresponding space, such things, is non-trivial. And studying the equation, and that's long process of studying convolution, we can actually say that cofactor L modulo gauge, this gauge by changing L by exact form, is actually an algebraic variety, fine dimension. Okay, so then actually, okay, so that's convenient representation. We can say that all rational integrals are quotients of some Killing tensors for some cofactor. Okay, so that's some simple but useful statements on relations. So now one part of the conjecture which I said before, so we consider the space of rational integral of fixed by degree and fixed metric G, then it's actually fine dimension. So let me give the proof. So if we try to approach the proof through PD system, it's actually very complicated, because you have to study compatibilities, bring to involution, and that's algebraically close to impossible. Let's do geometric argument. So at every so integral actually, since coefficients are analytic in X and in P it is algebraic rational, so every integral is completely determined by preimage of small neighborhood U in M. That's cylinder in tangent one, the local tangent, isn't it? So then we take a rational integral, actually fixed point. We even can shrink this U to a point. Okay, and then this integral become, well, then we freeze coefficient x's and we just get rational function. And rational function is determined by a finite number of parameters. That's precisely coefficients of numerator plus coefficients of denominator, that's those two numbers. Okay, -1 because we divide. Okay, that's those number of parameters. Okay, so f is homogeneous, so I can use this and I can say I don't need to work on the entire tangent bundle, but I can work on spherical, on spherization, or unit tangent. Okay, let me take n different points in general position, and number of points will be this n. Okay, and in addition, I have this point A where I would like to determine my integral. So how I'm going to determine this? I connect each of the point to point A by geodesics. Okay, so actually, I don't need even a geodesic convexity, so I can take broken geodesics here. So that's also fine. So integrals are constant along geodesics. Therefore, knowing directions of this geodesic gamma at the point AA gives value of integral f in the direction gamma at the point A. Okay, and so at the point A, I have n capital different directions, and I know the value of fz. And if point A is generic with respect to those points A1 to n, that those directions are also generic, and then I can uniquely determine my integral f. Okay, so that tells us that integral f is uniquely determined on at n set, and hence everywhere. Okay, by continuity. Yes, because I assume coefficient analytic. So this gives kind of let's give finite-dimensionality and a bound n square, right? Because having n points, I need n values in those points. This is a big number. It's definitely non-sharp bound. Okay, but it gives fine dimensionality. So, but even for flat metric, so that's too big bound. However, the proof actually shows that these finite dimensional thing is actually not only manifold, but it's actually algebraic variety, which is useful in other arguments. Okay, so let's now concentrate on flat metric, or actually on conformally flat metric. No, sorry, on projectively flat metric actually, because it's projective invariant story. So in other words, metric of constant curvature. So that's what's important here. Statement is that that's just ratio of Killing tensors, no cofactor L here. So P and Q are absolute Killing tensors. So that's their ratio, right? So if you go back to this thing, that's of course a ratio, but here P and Q could be relative with non-zero or non-cohomologous to zero cofactor L. But for flat metric, we claim that there will be no cofactor. And this actually, cofactor is something that makes difficulty in general in this conjecture. So because even though for each L, the space of relative tensors for given cofactor L is smaller than that for flat metrics, this space of cofactor is also can contribute to dimension a priori. Okay, so let me do proof. Let's start n equal to 2. Okay, I take just flat metric case. So that's Hamiltonian. And of course, for flat case, we have 3 Killing vectors, 3 leading integrals. Translation, translation, rotation. Okay, that's 3 isometry fields. These are linearly dependent. In the complement of the dual cone, Hamiltonian equal to 0. Of course, in Euclidean signature, this is just 0 section. That's not interesting, but you have to think also that the same proof applicable to Lorentzian case, or you can complexify, for example. So it's useful just to remember this. Okay, so there are 3 things, K1, K2, K3, 3 functions, but I have cotangent bundle, which is 4-dimensional. It has coordinate x1, x2, p1, p2. And here are 3, K1, K2, K3. So I add to those 3 functions one more, J, which kind of Liouville field, x1, p1 plus x2, p2. Okay, and then I would like to see transformation from coordinates x1, x2, p1, p2 to coordinates k1, k2, k3, j. Okay, because I have 4 functions, they are actually functionally independent everywhere in the complement to H. Therefore, I can find correspondence between them. That's algebraic diffeomorphism outside H equal to 0. And therefore, I can express this vector field, Liouville vector field in cotangent bundle through new coordinates k1, k2, k3, and j. And it's just Euler vector field in those coordinates. Okay, so what do we know? So we know that f is actually an integral, and therefore it should be expressed through those k's, because that's maximal number of k's here, right? So we talk about 4-dimensional space, cotangent space of surface, and curve has transversal or has codimension 3. Okay, so these are linearly independent. Therefore, okay, so also strong statement, they actually functional independent. Okay, so f should be a function of k1, k2, k3, and on the other hand, we know that it's of degree d in p in momenta, therefore satisfies the Euler equation here. But now we look to this equation, and they say that actually f is homogeneous polynomial just in ky, k2, k3, and no j. Okay, that's the argument for Killing tensor of degree d. So that any Killing tensor of degree d can be expressed through Killing vectors. Okay, that's the proof of irreducibility, that all Killing d tensors expressed through Killing vectors in the flat case in dimension 2. Okay, and modification of this a bit longer, doesn't fit my slide, but very similar idea works for rational integrals. That finishes case in blue. When n is greater than 2, the story becomes a bit more complicated because I think about even three-dimensional space. Then we have 6 Killing vectors. But codimensional curve in codimensional space is actually 5, right? So we have more killings than we need. So they will be CSGs, and we have to actually take them into account. There's too many integrals there. Okay, but that's possible to do. I will result of that, and the conclusion is actually that, of course, if you have this thing here, right, then we just count how many killing tensors of degree R we have, how many tensors of degree S we have, we sum them up, and we subtract 1 because we take ratio. Okay, that's it. Okay, so let's consider a very particular case. So here was general R and S, which is degree of P and Q. Let's consider the case when R is 1 and S is 1. Oh, that's a very simple story. That's called fractional linear thing. You divide linear over linear expression. Okay, and even we consider the case just in the plane, dimension equal to 2. So this was first addressed by Agafonov Alves. Alves was a student of Agafonov in Brazil. And this, they consider this problem in relation to reps. Okay, and they prove that we consider the space of such integrals. We already know it's actually algebraic manifold, prime dimensional. Then it has dimension 5 or 3, if non-empty. Okay, and honestly, the proof works for Lorentzian signature. One, of course, would not be surprised if it's true for Riemannian. And we have a bit different approach to this thing, and we will prove it for Riemannian case. But a word of caution. When you work with scaling tensors, doesn't matter what signature is, because equation is linear. So you can actually easily complexify things and say, you go to complex word, weak rotation, return back to real world with different signature, the same story. Now here it's not. Here it's not working like this because this equation is nonlinear, and you cannot easily complexify nonlinear problem. Okay, so that's formally you cannot deduce Riemannian from Lorentzian by the complexification trick. But anyway, so it's true, of course. Yes. So so here's the theorem. So the same story 5 or 3, if non-empty, but actually there's a group that acting on this PGL2. Because what do we talk about? So we talk about linear expression over linear expression. So functions type P1 plus functions type P2 in numerator over functions type P1 plus functions type P2 in denominator. But actually, let's just forget about functions. So one function follows the other function. So whenever you have a ratio of this kind, so we can actually apply it to it matrix A, B, C, D, right? So we think, that's not a ratio, that's actually a vector with 2 components. Multiply this vector by matrix, get a different vector, and then divide. Okay, so then you get action of PGL2. And we can do quotient because that's algebraic manifold and that's algebraic action. So it actually exists well-defined rational algebraic quotient. And it's a bit stronger statement than here. Then it's true that we just, in a sense, deduce the dimension 3 from it. Okay, so 5 minus 3 is 2, 3 minus 3 is 0. We can say a bit more precise. So actually, if dimension 2, that's precisely RP2. Okay, because it's projectivization of three-dimensional space. And what is three-dimensional space? Three-dimensional vector space is space of killing vectors. Those three guys, K1, K2, and K3. Projectivize this, you get precisely this RP2. Or if it's actually not constant curvature, then possible to have next dimension 3, and actually there will be just finite number of points. So we know dimension 0, but it's actually strong. Well, of course, you also know finite number because, as we say, it's actually rational algebraic varieties. But we can say it is stronger that it's actually no more than 6 points. I was not able to prove it's actually 6 is realizable, probably not. So I think it's either 1 or 2 that is sharp bound, but unproved. 6 is proved. Okay, so a bit additional to this. So if we still talk about fractional linear integrals and on surface, and of course one can say, let's look to surface of revolution, because the surface of revolution by definition has linear additional integral. And if we also in addition have fractional linear integrals, then we would have three, we would have superintegrability, but this never happens. That's the second statement. So if it's non-constant curvature, of course, for constant curvature we have everything. But constant curvature, all fractional linear integrals will be reduced. That's also interesting. So if you have a non-constant curvature, you have non-trivial fractional linear integral, then it's not surface of revolution. Okay, so that's about dimension 2. And let me now discuss a few examples, couple of examples. So that's kind of known metric. It appeared previously in several contexts. Also appeared in my old paper on linear integrability. So here's Hamiltonian indeed, right? So because it's just a conformal factor here, we have to take inverse matrix, so we divide by it. So this has no Killing vectors, but has 3 quadratic Killing tensors. One is Hamiltonian, and 2 others are written here, and I factorize them, so they actually consist of some factorization. But it has degree 2 in P. Okay, so P1, P2, or Px, Py, now by some reasons are denoted by P and Q. I don't know why, but okay, so that's the notations. P is momenta for x, and Q is momenta for y. In addition, this Hamiltonian has 1 cubic integral. And it's automatically reducible because the only way for factorization of 3 is linear times quadratic, and there's no linear. But you see actually some factorization. Okay, so there's linear times quadratic, and there's some 0 order in P term. And this tells that, probably we will have some relative Killing tensors, and of course we do. So actually, if one think about higher degree integrals, then there's no quartic. Oh, okay, there are, but they're all reducible. They're still, for example, products of those 3 quadratic. Yeah, they're precise products of those 3 things. So there are 6 quartic integrals. And apparently there's no fixed degree integral. I prove this under some assumption. Computation is long, but I'm quite sure about this statement because with some mild condition I rejected. Okay, so that's about polynomial integrals. Now rationals. Here rational integrals. That's fractional linear, right? And that's quadratic overlay in P variables. Okay, this case was actually considered by Agapov-Shubin in different coordinate system, and G1 was found in there. Okay, so we revisit their work here. And let's observe that we actually have, for this Hamiltonian, that actually we have some relative Killing tensors. Linear, 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 quadratic. Okay. And then we have cofactors. And there is just 2 cofactors. L minus for R1, for R0, R2, and R3, and L plus for R1. Okay, so here formulas for L minus and for L plus, they're not inverse to each other, even though notations L minus and L plus, but they actually cohomologous to inverse to each other. So namely, if you take Poisson bracket of H with this function of x and y, okay, then we get this thing. And that's precisely the differential which we use in modifying cofactor L. So that's cohomologous L minus to a new function L with minus and L plus to the same function L with plus, where L is this function. Okay, so L is cohomologous to L plus and minus L is cohomologous to L minus. And now, since we have things minus and plus, we can produce, of course, by division or multiplication, we can produce new integrals. Namely, R01, R1, R2, and R1, R3, these products give polynomial integrals. with certain cofactors because due to this change. Okay, with certain factors which are explicit, but I don't want to write them here. Right, it's due to we have to change a cofactor to cohomologous, which are opposite. Okay, while the ratios give rational intervals, and it's precisely those G1 and G2. And then when we know this, actually this G1 will be this ratio of two actual integrals. So of polynomial integrals, F2 and F1, right? So F1 and F2 are polynomial integrals. Polynomial, again, in respect to momenta. And G1 is a ratio. So it actually should not be co-reducible, right? So it's ratio of killing tensors. However, in a sense of as law, it is still reducible because, well, because it's not ratio of something of degree less than 1, because that's impossible. It's already fractional linear, right? So in order to do this ratio, I have to go to higher degrees actually. And then turns out that higher degrees are factorizable with the same factor. When you divide, there's cancellation. So that's one example. And let me give one more example, which is kind of version of this. And let's just go back to first example. Look, the factor of the Euclidean metric is x squared plus 4y squared. By the way, this 4 is sensitive. This 4 is sensitive because the 3 quadratic Killing tensors. Yes, it's super integrability. So if you are not careful about 4, it will not be. It will just be Liouville integrable if you put here arbitrary constant. Okay, so let's change degrees here. Okay, x power 4, y power 4, but keep the same factor for that. It was also considered by a couple of sugar. So this metric, it possesses no Killing vectors and now no cubic integrals. Okay, so we raise the degree of this conformal factor. Of course, there was no Killing vectors before. There's no here. That's not surprising. But cubic integrals is gone, and number of quadratic integrals also becomes less. Okay, so still Hamiltonian, which trivial quadratic integral, and only one here. Okay, now we look to relative Killing vectors of which are linear. Okay, so linear in momenta. And functions, let's impose the condition that they are polynomial of degree at most 3. So here are all of such. Okay, there are 4 linearly dependent. Some coefficients, polynomial quadratic in x and y. So here actually cubic. And then the corresponding cofactors for those relative Killing vectors are the following. So 2 of them are equal. And then L3 is equal to L4. L2 is not even cohomologous to any of them, but it's cohomologous to minus L1. Okay, and this allows us to produce new integrals. And so we can get integral F2 by multiplication and multiplying by some function of x's, and also doing division here. So here we have, well, again, super integrability, and we use this theory how to obtain rational integrals. So many more explicit examples in recent works. There was a series of work by Agapov, Shubin, where they obtained new metrics with new rational integrals. Okay, so I think it's good for me to stop here. So very short literature. Okay, citation only of myself. But lots of citation. I mentioned a lot of people and lots of other people whom I didn't mention. Some of citations can be found inside those papers. So I think I will stop here. Thanks for your attention.
Okay, Boris, thanks a lot. Quite non-trivial. Questions, remarks? No question, no remark.
May I ask a question, please?
Yeah, sure, sure.
Boris Serafimovich, could you please go back to page number 7?
Yes.
Yeah, thank you. So you mentioned that it is possible to construct Hamiltonian systems, integral Hamiltonian systems with magnetic field.
Yes.
Has anyone already done this, or is it still open?
No, I just mean this one example of Machevsky Przejrzyska, right? Because it's you take quadratic and you take linear. As one as two.
Yes. I have seen that example, but nobody has done it with magnetic fields, right?
No, I don't think so. Actually, no. It's standard symplectic structure. That's correct. Yes. But
Okay. Yeah, thank you. Yeah.
No. I think you're right.
More questions? Okay, Boris, thanks a lot. Please send, if you do not object, slides to Arik. Okay?
Arik.
Yes. Thanks a lot. So, thank you.
Okay. Thanks, everybody.
So next time, Rafael Vitala. Thanks and goodbye.